Hello, hi Satya, can you hear me? Satya, can you hear me?
Hello, Ali. Am I audible?
Hi Satya, yes, I can hear you. Could you please try to share your screen? We'll quickly check your presentation access and everything.
Yeah, sure, sure. Yes, my screen is visible.
Yeah, cool. Great. Yeah, thank you. I'm reverting back to the previous screen.
Sure, sure, please.
Good afternoon, everyone. Thank you so much for your time and patience. The meeting will begin in the next couple of minutes. Dear all, welcome to the CATFM Virtual Technical Training Series. The topic for today's Virtual Training Day 4 is Charging Medical Electronics with Simulations to Deliver Patient Safety and Device Efficacy. Before we start this, let me give you a brief introduction to CATFM. CATFM is the world's oldest and largest channel partner to ANSYS with more than 30 plus years in the simulation industry. CATFM has grown as a system house by providing end-to-end simulation solutions ranging from software, hardware, consulting, support, and trainings. CATFM India, together with ANSYS, organizes a series of trainings for biomedical engineers across India in association with Force Biomedical for the benefit of the biomedical engineering community, which in line with our vision of providing better healthcare to all. So let us understand a bit about the topic before we dive into it deeply. The concern for medical electronics is definitely more pronounced towards patient safety. Electromagnetic radiation can mutilate a patient's health by acting carcinogenic, or any medical device which is a wireless sensor and actuator network can experience potential malfunction due to electromagnetic interference, which we call EMI exposure. Besides conceptualizing the advantages of electromagnetic simulations, for these applications, this training also details the general scope for simulation-based parametric optimization of antenna design as well as antennas printed on complex PCBs. So without much ado, I would like to introduce you to today's speaker, Mr. Kumar Satyavrat Sahu. So Mr. Kumar Satyavrat Sahu has 6 years of experience across academic and industrial vertical in computational electromagnetic tools. He started his career as a research fellow in University Grants Commission, and he has nurtured his skills in the field of antenna and PCB simulations, including EMI and EMC issues. Moreover, Mr. Satya has published articles on microwave structures in the journals of repute. Not only that, Mr. Sahu is the recipient of the Certificate of Excellence in Electromagnetic Olympiad from IEEE APMTT Society of India. Currently, he is contributing his skills to CAD India as a senior application engineer. I'm pretty sure that he adds great value in today's web training session, and you all can feel free to ask questions. Well, in the interest of time, all your questions will be answered towards the end of this session. So please note that this session will be recorded and shared with all of you. In case if you do have any questions during the webinar, please mention all your questions in the chat window to the host only. So thank you very much, Mr. Satya. Now over to you.
Thank you, Ali. Am I audible?
Oh yes, you're audible.
Okay, just give me opportunity to share my screen.
Okay.
My screen is visible, right?
Yes, your screen is visible. Yeah.
Okay, great. Yes. Okay. So thank you, Ali, for a very good, nice introduction towards the participants. I believe definitely they will improve their skills from this session, and they will nurture their skills. Okay. So I welcome all the participants. Patient safety and its device efficacy. First of all, we'll understand what is charging medical electronics with simulation. Charging medical electronics means we are developing the electronic part with the simulations, and to realize the patient safety so that without deteriorating any kind of patient's health conditions and bringing into a normal sustainable life, what are the devices we are implementing and how the electronics is we are improving day by day with simulation. That's what we are going to see on the presentation, okay, over the period. So based on that one, here is my out need of wireless connectivity in the healthcare, okay, because now we are moving towards the 5G generation and everything will be connected towards the IoT is Internet of Things. Similarly, what are the tools that we are using for user equipments? Let us assume that we are using a mobile phone or a Fitbit or any kind of wireless thing. How we are going to develop that one? Not only that one, how we are those devices are connected to the base station. Okay. Similarly, what are the medical and wireless device trends? A smartwatch as application example. Then the importance of SAR over here. SAR is the nothing but specific absorption rate. Okay. Then what is the how it HFSS can be used? HFSS is nothing but the simulation tool is used for cancer treatment. Similarly, for EMI pulse generator. Then finally, we'll be moving to how we are going to design the reliable electronics. Basically, what are the challenges we are facing in the bringing the best device for the medical industry and concerning the safety as well as the reliable electronics so that it will run for a longer time. So when it will be interacted with the body, okay, a body in the sense of human body. Then finally, we will talk on the conclusion. What are the things that we have takeaway points from the session? Okay. So here I'm moving to first session. So meanwhile, I'll be giving gaps of for little bit Q&A and discussions. I want everybody to involve in the presentation and have a quite interactive session. Okay, basically you will be writing the questions to the host, and I will be answering in the between in three phases or one phases or something like that. Because it's a two, we have taken a gap of 2 hours of time, so we'll be giving little bit of halt. Okay. So So right now, as
Satya, your voice is breaking in between.
started SMS service and all. And finally, we moved to the internet service, voice, text, as well as internet. So all these things are we have connected over the internet. Then finally, all multimedia, internet, everything will be facilitated with the 4G. But finally, the world is moving over like within a half of a decade, the world will be connected through the 5G services. Means here everything starting from the wireless technology, smart parking, a car to car communication, and what are the apps, the applications for a smart home beyond our imagination is going to connect it to over the internet, so that you will have a regular connectivity to your devices, the electronic devices, and you can monitor anywhere in the any corner of the world. Okay, this includes smart environment, IoT technology, self-driving cars, and many more. So, to provide that kind of scenario, a 5G scenario, we must have a two things. The first one, the user equipment, how user equipment has to be built properly, and the second part, when the wireless user equipment, it has to connect it to a base station, right? So we have to see that how both the things can be modeled properly. So if we are considering the user equipment, first of all, then it contains wireless connectivity. The first parameter is the antenna design. Then how the antenna is integrated, whether our antenna that is there, that is properly optimized, is that optimized or not. Means the optimized product will have a better performance, so that, and very less cost, so that it it goes for a longer time. Then sensitivity analysis, the statistical analysis, all the things. Not only that one, then how it is being interacting with the human body, basically the power density, whatever the field that is coming out of the wireless device. Okay, that how is being interacting with the human. Okay, similarly, when we are coming to the base station, means this user equipment will be connected to the base station, and how this base station, because it is the not only the providing of the user equipment, it is also important that how you are providing the network also. That is important part. So in order to provide the network, basically we call that one as a base station, where all the user will be connected. Okay, so in that we have to see phased array analysis, statistical antenna elements, what are the radome placement. Radome is nothing but a one cover over the base station that provides from a bad weather conditions, any kind of deterioration of the you can say equipment. Then how it is being beam forming. Beam forming is nothing but a rotation of the beam, and how is being means on the real time moving effect. So we are going to see that one. First, we'll be focusing on user equipment to see how it is being developed. Then finally, we'll be talking about the base station part. Then we'll be talking on the how we are going to design the reliable electronics. So first, so basically the things are divided into three parts. This session, the first session will be first phase. In the first phase, we'll be covering the user equipment only. We when we are coming to the user equipment, okay, and user equipment might be a Fitbit or a pacemaker which will be connected to over there, or it might be some kind of pocket watch or wireless or pedometer. Okay, so all these things will be connected wirelessly, and it has to be pointer means placed on the patient body. So that's why we call that one as a, we adopt as a biomedical industry, we take as a P4 medicine. P4 is nothing but 4 P's. First is the preventive, second is the predictive, and the participatory and personalized. Okay, so in order to see the monitor properly, every time the patient cannot go to the doctor, and he or she cannot stay for longer time. But if the patient will have a certain wireless device, okay, and he will have a near him wherever he goes on the harsh environment, or he is doing any kind of physical activity and all that. So all this data, suppose a pacemaker is there, or a heart rate sensor is there, so that data will be connected to a mobile, and to the mobile it will have internet access, so that a doctor in the any corner in the world will have access to that one. This will reduce the saves many of your time. That's the beauty of wireless connectivity. So that's why we need a we are moving towards the world where wireless connectivity is the most important part in the healthcare segment nowadays. Okay, so that's why we are going to design a medical and a wearable device trends. So we have to see what are the device trends in the wearable part. So we are going to see a simple fit or a smartwatch. You can see faster as well as low power devices. These are going to operate in 1 volt or 1.5 volt, and at the same time it has to be integrated on a very small, so that it will have a very small size, and the miniaturization is also. Then finally the cost sensitive analysis. We have to bring out the best optimized product so as to for go for longer run at a very less cost. Similarly, the emerging trends, it's not only limited to the smartwatch. There are many other devices that will be connected to the human body for a patient or a this one I have taken an example of a sports athlete, where we are seeing we are putting a sensor over here at this way, and where we are monitoring what are the best conditions and what are the best health conditions, basically the bone conditions, the fit, how much the pressure is there, what is the temperature of the body, everything will be connected to the one system, which he'll be connecting as a simple mobile, and we are seeing the what is a uh, we are seeing the patient's health over there. Similarly, it's not only limited that one. It's not limited to the only the patients only. We are seeing a big. What are the use equipments that is there in the medical trends, like a MRI machine or something. Those machines will be also sending the data wirelessly to any corner of the world. Okay, so that's the beauty over there. So that's the importance of in the you can say 5G world, or you can say where all these devices will be connected. Similar, we have taken one of the very common example. I believe everybody will be aware of a smartwatch or a Fitbit. Okay, so if you are going to see in the Fitbit, there will be a small PCB with a microprocessor and an antenna over here and all that. So the wristband will perform the following things, like monitoring the blood pressure or the blood rate. Similarly, it has to be connected to the Bluetooth, to see sending wireless signals, and finally a small LCD panel display to show the what are the like blood pressure and all that. So that in order to provide this part, there will be a the key those are like omnidirectional antennas, because one antenna will be there which will be sending the signal. A small 3-layer board of a 4 centimeter, and finally a wireless power charging mechanism. So what are the mechanical challenges we are going to see is the impact resistant. The material should be so designed that whenever it falls from our some certain distance, it should withstand on that one. So, and the manufacturability, the design appealing feature of the and finally it has to be a comfortable to wear, right? And the other part is the basically the embedded part is that not cutting with the control system part, where we are going to control the two wireless system simultaneously and generate the robust code to ensure accurate and measurement display, because though no doubt there will be a sensor which will be measuring, but whatever the embedded system will be there inside the thing, they will be taking the data properly, and they has to provide a proper data. So that's the also important part, which will be done by the embedded coding part. So here we are going to see, this is a small antenna over here. We are taking that as means from this one, we are going to see the smartwatch is there, and in this smartwatch there are two antennas. You can see these are the two antennas. One is the Bluetooth antenna, another one is the biosensor antenna over here, and that will be connected to the smaller. And we are going to see how this antenna is going to perform. So the Bluetooth antenna is going to perform on the 2.4 gigahertz to 2.485 gigahertz, and the return loss should be less than minus 10 dB. Basically, this is standard we are taking to get the proper wireless data. Okay. Then finally, it has to be integrated with the flexible substrate. Okay. And the biosensor antenna. Here are the two systems. One system is the Bluetooth antenna system, and the biosensor antenna that will be operating in the 400 to 450 megahertz. And the return loss, same criteria we are fulfilling, and it has to be embedded in the flexible substrate. Okay, so we are going to see, once we are analyzed the antenna over here, you can see over here the same antenna is being integrated on that system on the same Fitbit or the bench, but the antenna is going to perform on a very straight properly. But the moment we change it into a conformal structure or the very non-planar structure, you can see there is a shift in the frequency band for both the antennas over here. So these are simulated results that we have got over that one. This one is for the biosensor antenna, and this one for the Bluetooth antenna. You can see the moment we wrap on that, there will be a change in the feature. So based on that, based on the releasing after a conformal structure, we can see how best we can provide a conformal structure so that our antenna should provide a much more better way. Okay, so here in this criteria, we are fixing the two parametric problems. We are optimizing it as well as not only to the design but towards the conformal structure also. So that can be done only through simulation. You cannot every time fabricate and design it and send it testing and again redesign the hardware. So that all these things can be done through a very good and a gold standard simulation software. So, so what our tool, the ANSYS tool is providing. So ANSYS is nothing but HFSS, or we that's called high frequency structure simulator. So it contains more than 100 to 120 plus topologies of very standard antennas. Standard antennas in the sense a bow tie antenna or a simple monopole antenna or a horn antenna. Everything will be there pre-designed, ready to make solve. We just need to give the frequency band over here, and finally we'll be getting a ready to solve model over here. Okay. So it will create the means the user or the engineer need not to design always. Okay, he can use the for the standard antennas that already the scripts are there, build its own. Okay, you can see over here there are numerous types of antenna. So depending on the requirement on and frequency band and all, we can design also. That's the beauty over here. It's not only very limited to a very small structure, but you can design to most complicated structure like spiral or a biconical or a log periodic antennas or a horn antenna. Everything will be designed. But if you have your own proprietary antenna or a patented antenna, then you can solve that model also by importing inside the tool. Here I've taken one example of a simple dipole antenna. It's a very standard practice, and we are going to see we are just going to give the frequency band over here and what are the boundary conditions, and we are just giving the input details, and it creates a ready to solve model. And we are going to create what is the S parameter. Basically, S parameter is the scattering matrix we see, and at the frequency band on which it has to operate, it has to perform less than 10 dB. And finally, we are going to see what is the radiation pattern over that one. So the radiation pattern is basically the electromagnetic field that is coming to the space, spatial space. And what is the real field communication? or the near field, the electric field, the magnetic field, everything will be there. We can see in those visualization, so as to see what is the physical behavior of electromagnetic waves on that structure. We can see that part also. Not only limited that one, we can, since we already the models are there, we can parameterize that models in order to tune properly, in order to optimize it. So this creates this antenna design. We are going to create a very accelerated and interactive real-time tuning design. It is the one of the most efficient method used for tuning and sensitivity studies for and optimization. So basically, we have analyzed based on the script and all that. So we are going to see by changing different dimensions, length, width, and what is the gap between these things, depending on input power and all that. We are going to see what is the best performed antenna, and we are going to see the what is the S parameter. So this is how we are going to optimize, or we can say tuning of the antenna, and we can see the what is the sensitivity analysis also. So here I'm running a one video over here, so that will give very brief insight of how user equipments are important and how user equipments are being used to a very common world by different environments and different across the different industry, and probably from biomedical industry or eye care industry or you can say autonomous industry. Ali, can you unmute yourself?
Yeah.
Yeah,
Yes, sir.
just confirm me if you are able to see the audio, able to listen the audio part. Are you able to listen?
Not exactly. No, I'm not
No.
able to hear that audio.
Okay,
Yeah.
I believe there might be some kind of a glitch. That's why I'm unable to. But still, I'll be reiterating what uh, this video is all about. I'm losing the video over here, and meanwhile, I'll be talking.
Yeah, you can describe that, the
Yes,
whole.
yes,
Yeah, cool.
yes. So you can see that the Internet of Things will be uh, yeah, the Internet of Things will be connected to smart energy environment, automotive industry, where we will be using a wireless. And if we are putting an antenna over here, and how it is being the electromagnetic fields are being the products, then we can put the wristbands over here. And similarly, if you are going for a very smart contact eye lens, all these things can be also analyzed in the IoT part. And companies around the world, they are creating the Internet of Things from all across the same industry, starting from the healthcare, electronics, well as uh, uh, as well as the energy, all the things. So before also fabricating, we are going to see the best performance. So this is the example of a wristwatch which I was discussing. You can see over here the wristwatch has been designed over here, and we are going to see the Bluetooth and a biosensor antenna as well as the Bluetooth antenna, and how it is being connected to Bluetooth to connect the audio, and how we are going to design it over here. Okay, we are going to see the planar performance as well as the normal. We are taking two antennas over here, and we are seeing what is the wrapped performance also. Okay, we are going to see what is the radiation pattern, what is the behavior of different frequencies, and what are the in the different operating conditions. Okay, and we are going to see what are the field behaviors. After that also, we are bending the structure in conformal structures, okay, because this is the mechanical part also. We are seeing what is the change in the performance of the antenna after the conformal structure. We are going to see that one. It's not only limited that one. We have a PCB complicated structures over here that will be connected with operators like SD memory card and the 3.0 USB, everything. So all this analysis can be done using IC and IC packaging analysis as well as the PCB analysis, basically the signal integrity, power integrity analysis to different tools at different levels. Okay, here for a IC analysis, we are using Red Hawk. For a IC packaging analysis, we are using as signal integrity wave, Q3D, HFSS, and for power integrity and signal integrity of PCB, we are using same SI wave, HFSS, and Q3D. Okay. Yeah. So while doing the electronics part, definitely it is operating with certain power, but with longer use of time, definitely it is going to take a, it is the temperature of that device is going to rise up. Okay. So that's why after doing the HFSS analysis, we have to do a thermal analysis. That's the important part, because otherwise it may give out a burnout. That's why this watch has to go through a multi-physics analysis. Okay. So the multi-physics analysis gives the ability to do electronic analysis as well as the thermal analysis over here. So we are going to see all the things. Now, we are going to calculate the operating temperature through the steady state thermal analysis in the ANSYS Workbench platform. The other part, we are going to put the same wristwatch in the different environments, like you are operating in a different, and how this radiation, whatever the radiation that is coming out of this environment is going to affect on other devices. You can see over here, this guy is taking, yeah, just give me a second. Yeah, this guy is taking a wireless Bluetooth speaker, which is putting on the head, and a Fitbit band is there, and how these multiple wireless features are going to interfere with each other. We are going to calculate that. We can calculate that one also. I believe you are able to visualize through the animation what it is talking about. We have multiple environments. It's not limited to. So similarly, you can bring out your own other electronics like pacemaker or a speedometer, wireless, and we are going to see the performance. Similarly, if moving to autonomous vehicles, the wireless things are being put in the on the front bonnet of the of the car. Okay, we are going to see that one simultaneously over here. Yes, you can see over here, these wireless sensors are there, and those are connected with base station. And we are going to see what are the performance of these devices by putting the sensors. And all this data will be sent through wirelessly. Yeah. So when it comes to the safety and the biomedical one, because we are taking preventive measures also, not only limited to the patient safety, but also how the preventing measure can be done. Suppose a car is suppose an autonomous vehicle is moving and suddenly a person came, how the car is going to detect, or while a driverless car, if we are going for a driverless car, then how this car is going to detect an object over here, that can be also analyzed using the tools. Just give me a second to play the video. Yes, yes. Yes. What it does over here, basically, there will be an antenna that will be putting a signal over here, sending the electromagnetic signal, and we are going to automatically see based on that if there is an object is there, that signal is going to reflect back, and we are going to see yes, there is an object is there, and the autonomous car automatically detects it. And these cars are equipped with very large touchscreen and embedded products to understand the code is so designed that yes, that can be designed. And based on the what are the screen touch, the LCD panels, everything has to be operated through, and we can analyze this PCB panels also. Yes. Yes. So similarly, if it comes to the smart home technologies, you can see over here, there will be not only car, there will be multiple systems that will be connected. So all these things can be analyzed with you can see over here, just give me a second. Yes, you can see over here, all these things, smart wireless part that can be connected through wireless to one common base station, and we can analyze in the smart home. And this technology, wireless technology, can be implemented in the smart home, and we the engineers in the 5G world contribute to the most in the wireless industry for a best and the preventive as well as the to maintain the safe environment. So there is one because since we are going from a very small structure to very large structure, and we are putting the very small structure, and we are going to see a very on a very large environment. So we have different technologies to solve that one, like full wave solver and hybrid solver and asymptotic solver. All these things are done because our antenna so our antenna will be a very small structure, but when it's keeping to car bonnet size, a front panel, definitely is going to take a very big, and it is going to consume very long amount of simulation time. So we have very full hybrid methods are there so that we can solve our best performance in a very less time. Okay, to bring out the most effective product world. And yes, so similarly, all this technology can be implemented from multiple systems so that the radiation we can see the analysis and to the different world. Now moving to connected healthcare. Yes, so here we are analyzing a smart eye lens so that all this whatever the data what our eye is seeing is being sent to the wireless part, and we are going to see what, and it's always cannot be solved mathematically. It has to be analyzed to a simulated so that we can see what is the best performed analysis and to see different and operating conditions, and we can use it for laser surgery and all. So many things can be implemented with different innovative ideas over here. Okay, so that thing can be analyzed. We are bringing a similar kind of eye contact lens, and we are creating a same environment virtually, and so that depending on the different conditions of the real environment, the same virtual conditions can be implemented for that lens, and we can bring out a fidelity model for different. And all this data can be wirelessly connected over the base station servers, and so that the data will be stored and can be accessed to a different worlds around the globe. And all data what will be generating will be moved, encrypted and secured throughout to the servers, and it can and kept in the cloud so as to so that it will be a rest usage. Okay, and we can see predict, and we can predict after surgery also what will be the outcome. Also, that same thing can be analyzed. So basically, IoT or the 5G or the wireless connectivity are being most of the trans is that mostly can say game changer or most important things that is in the coming world. It's not only limited to yes, not only limited to home appliances, automotive or anything. It can be implemented to holographic televisions, 3D for printing, wearables. It can bring out the smart cities, and which we can access through smart communication through and anywhere in the world in the through our smartphones, most common equipment. And we can see over here, IoT can be implemented to any wireless meter or wireless band, a user equipment. All the things can be connected over the board to bring out a higher fidelity model. And the glow will be very small in the coming world over here. And we can access the data anywhere in this world. This brings end of the video, and since as I told, I'll be taking a three-phase session over here, so I came to the end of first phase. So I would like to take any questions from your side. If you have that, please feel free to answer. Upon this session, this phase, I'll be bring out the second phase.
Yeah, thank you, Satya. Well, in case if you have any questions, you can drop your questions to the in the chat window to the host, or even you can unmute yourself and you can directly ask to the speaker. Any questions or something that you to explore more on.
Come on, come on, participants. I want this session to be interactive, not a one-sided session. Please feel free to ask any type of questions. Any question is a question. It doesn't matter how it is or how big it is or how small it is. Come on. At least I expect one question from somebody. This keeps me motivating, man.
Well, Satya will wait for a minute. We'll see in case if they have. Yeah. A question from Navya. Sir, how much will be the strength of the security of data acquired from such smart devices such as contact lens?
Okay, so whenever we are going to deal with, it comes in the category of how our programming is there. So since we are using a 64-bit, but for the server it's 128-bit. Right now, our whatever the data is with the banks, it's a 64-bit data. But when it goes to the server and all that, it will be very highly secured and it will be encrypted to 128-bit machine. And for that, a hacking or a cracking those data will be very tough for any kind of hackers. No doubt, all these wireless data will be stored in the very secure soft in the secure servers. Like Microsoft Azure is implementing a cloud implementing. Similarly, Amazon is also coming. So all this, they are giving up data centers, and all the data centers will have a very good conditions to store your data so that it cannot go to any kind of wrong hands or so that they cannot be used. So that's the safety. I believe there are companies like Google, Amazon, Microsoft. They're working on the most secure system in this world that is coming in coming decades. Okay, it's not only limited to the physical data center. Microsoft is working on a data center that is beneath the ocean, so that to maintain the temperature of this. It means Microsoft is working on those things. So you should be stay assured that all your data, whatever you are storing in the cloud through wireless connectivity, will be secured. Though you should not worry about this one. And I believe Microsoft, Google, companies like Microsoft, Google's, and all, they are assuring that thing also.
Great. Yeah. Thank you, Satya. And we have one more question from Mohammed Yasin. Sir, can we design the total architecture of a circuit with simulation?
Yes, definitely. You can design. Okay, you can not only design the complete architecture, but you can analyze it properly also. It's not only restricted to electronics part. You can analyze mechanically as well as the thermal aspect of that one. Very in the next, I believe that is there in the third phase of that one. Okay, probably in the third phase of the session, I'll be covering that one.
Uh, Thank you so much, Satya. And in case if you have any questions, you can drop your questions in the chat window. You can get quick resolutions for all your queries. Yes, Satya, I think it seems we have only these questions. Yes, we got a question from Harini. So what is the common material should be preferred to use for the biosensor?
Okay, so generally for biosensors and all that, since the sensor, see all this wireless wire things means wireless thing. It's a metallic thing, so it will be designed of the copper, but it has to be printed on some kind of printed circuit board. It's like it must be a flexible part. So it might be a PTFE rosers, or it might be a PCB material, or you can say it's a very flexible dielectric substrate. Okay, of very less permittivity. So those are there in the market. Okay, so that comes in the category of material science. So these very biosensors material modelings are there already for the standards. I mean, the standard has been declared like the Rogers and PTF Teflons. There are many materials are there, and not only limited to that, those material properties are being implemented in the simulation tools, and you can use those material properties to while defining or designing your structure. Suppose you are using a Teflon or some kind of a carbon, you can say a carbon nanotube material kind of thing, or you can use a steel, anything. So there are many materials out there, and you can, depending on your requirement of your whatever for your availability in the market. Okay, because we have to bring out the best commonly available material with a very small cost, right? That's also important part to do the cost benefit analysis. So those parts, depending on the availability and all that, you can use those materials in while analyzing in the tool.
Sure, Satya. Thank you. And yeah, thank you, Satya. Probably you can go ahead with the second phase.
Okay, sure. So since in the first phase, as I promised that I'll be in the first phase, I talk about the user equipment side. Okay. Now I'll be moving to the second phase of the chart, how we are going to design the base station part. Okay. Basically, base station is being used where it will be accommodating all the things. Like if you're using a cell phone, right? Definitely from in your nearby locality, there will be a tower. All right, a cell phone tower will be there, and this cell phone tower will contain many antennas like circular dome structure and all that. Basically, those are nothing but the phased antennas inside there that is going to provide the network for your user equipments. So it's not limited to the only user equipment. We are worrying about the also base station designing part. Okay, because base station is going to provide the network for these equipments. So simple. The base station is nothing. It's just an array antenna because in the device, one antenna will be there. But in the base station, there will be multiple array of antennas that will be providing a very high power and a high beam. It's like making if your multiple signals are there, then due to constructive interference, it will going to bring out a very high directive beam over there. And depending on the interference and the phase of the different devices, the beam can be tilted. Okay, so while designing the array antenna, the directivity has to be calculated, and not only directivity on one direction, it has to be connected in the different directions. Okay, so what we are doing over here, we are going to analyze that antenna. Okay, and so in the traditional workflow, what we do, what the engineers are doing over here, the traditional workflow antenna, they are going to analyze the antenna, and we are going to put a mathematical expression that what is the difference of there, and based on the error, what is the number of, we are going to compute. It's a simple algebraic expression. For this one is for the very infinite array, if the number of elements are infinite, but there is a limitation inside this analysis. But once we do that, this is a mathematical part, but at the practical part, this analysis will be a little bit challenging. And for that, this antenna array factor is making an important impact over there, depending on the depending on the single element behavior. You can see over here, suppose if we are giving a 0 degree phase shift, 0 degree in the sense if we are giving a 1 watt signal and a zero, because every signal will have a power component and as well as a phase component. Okay, so suppose we are giving a single power and with a zero phase, right? You can see over here the beam will be completely perpendicular to straight. The moment we change a 15 degree over here, you can say the beam will be tilted little bit. Similarly, 30 degree, the beam will be tilted little bit extra. Okay, so this is how we are going to design for a conventional array antenna analysis. Okay, you can see over here for a single antenna, what is the performance for a 5x5 antenna. Okay, that's if this is array structure of five elements in the x direction, 5 elements in the y directions. Okay, the antenna behavior changes over here. Similarly, 10x10 antenna, that we will be getting a higher beam pattern. Okay, but the same if we are going to increase furthermore, you can see a highly directive beam over here. So array antenna creates a very focused beam. So it's not only because our antenna is not going to focus only one direction, right? It has to be rotated on different directions. We can see over here the same array antenna we have taken, a 10x array antenna, 0 degree, which is showing that one. But at the 15 degree, the performance is little like that, and 30 degree, the antenna directive is like that, and at 45 degree, you can see over here the side lobe levels for a directive beam is quite less, similar little bit less. Here the side lobe has been increased, and the 45 degree a further increase in the side lobe. So if you are getting a side lobe over here, then it's a loss of power. And definitely it is important that our whatever the power we are sending, it has to go to the maximum in that direction. So that's why we analyze these antennas, okay, so as to give a high power in a particular direction. Otherwise, it will be a loss of power, right? So that's why we have to do an analysis. So in this tool, we have something called finite array domain decomposition method. So what we do over here? So you can see over here, we have analyzed one antenna and the same mesh is being copied multiple times. Okay. You can see over here, taking a simple 3x3 element and we are copying the mesh. Okay. And finally, we are getting the analysis of that one. Because mesh is an important factor in order to analyze any kind of structure. So that's why once we have designed an optimized mesh for single element, the same mesh can be utilized for different element, for same structure kind of elements to bring out the higher fidelity, or you can say, yeah, antenna analysis. Just give me a second. Okay. So I believe you are a little bit of aware that how base station antennas can be analyzed. So I believe you must be aware. Just give me a second. I'm muting because there is a noise over here. Just give me a second so that I can mute over here. Just a couple of seconds, Ali.
Okay, Satya, sure.
My sincere apologies for the delay because there is a noise, so that I have to, since I'm working from home. Okay, I believe that shouldn't be making any kind of concern. So I was talking about that how the mesh is being copied at the different directions so as to bring out the higher fidelity models over here. So what we are achieving over here, since if you are copying the mesh in different directions, it reduces the simulation effort. And since the already for single element the results are there, and the same results can be used for mathematical calculation to bring out the analysis. Okay, so that the one beauty over here, since right now you might be seeing that our machines are coming with a CPU like 2 cores, 3 cores, 4 cores, 8 core machines. So the same mesh can be used to calculate on a different cores, and those cores can be used for analyzing to distribute the domains and to bring out the results. Okay. So if you are using a higher core machine, the domain will be completely decomposed. You can say decomposed, or we can say it's a kind of parallel processing we are doing over here, and that can be analyzed most properly. Okay, so here is the animation for a 8x8 antenna. You can see over here a small antenna is being analyzed, and the same analysis can be copied. Okay, here we are copying that mesh at different locations. Okay, to create an array so that can be analyzed through electromagnetic simulation, and it solves the electromagnetic equation in the finite element method. Okay, so depending on the requirement, we can hide the antennas. Suppose depending on the requirements, like if we have very sparse antenna, so we can hide those elements. Okay, for the mesh. So and design our, and finally we'll be getting a what is the radiation pattern of the array antenna depending on what is the antenna array structure. Okay, so we can use a different excitation method, and we can put a different phase angles to bring out what is the antenna directive lobes and all. You can see over here, this is one of the example that we have taken. Okay, uh, it's an 11x11 monopole array antenna, and whatever the results we are getting, we have taken that paper. It's IEEE paper, and it is indeed a transaction paper from Antenna and Propagation Society, and that one we have taken as standard. And whatever the analysis we did through the HFSS, okay, our tool, and whatever the dotted line, it is from our analysis. Okay, it's a measurement value with, and the solid line is from the simulated value, and we are getting exact correlation. Okay, whatever we are getting for the array antenna analysis. So this is one of the examples that I've shown. Similarly, for depending on the companies, like different companies are there, and providers, they are doing very good research on optimizing these antennas, base station antenna, to create a hybrid, to create a very robust structure. Okay, it's not only robust structure creating at a it is in one frequency, but it has to accommodate in multiple frequencies. So multiple frequencies in the multiple antennas will be integrated, and we are working on towards those kind of antennas also, array antennas. So we call that one as a phased array antennas. You can see over here, it's a finite array analysis. You can see over there's a hexagonal kind of shape, and we are seeing what is the phenomena of a radiation pattern behavior of a finite array. So this is how it looks like. So what we are doing is we have taken one antenna, and we have created one 16 structure, and depending on the size, we are activating and we are deactivating the elements. You can see over here, whatever this analyzed antenna is kept at the center, and few elements are in the light blue color. uh, those are being activated, and whatever the hidden part, or you can say in the grayish color, those are not activated, so that we are creating the similar kind of a rhombus structure. Okay, so this is you can see over here, we are creating a 15 cross 16 array mask with 240 cells, and in the 240 and 128 active cells. So this, all the cells are completely active, and you can see over here in the finite array domain decomposition method, we are exciting with 512 excitations, and you can see over here in the distributor we are using 148 gigs of the RAM, and the solving time is just about 2 hours 3 minutes. Okay, but if we are going through a conventional analysis for this kind of very big structures and factor, definitely it is not going to take less than 5 to 6 days in a server or a very high performance computing system. Okay, so that's the beauty of a domain decomposition method, what we are designing over the for the base station. You can say what is the behavior of a spiral antenna, small spiral antenna. That's the size of you can say shape of 9 cross 9 array. Here we have given a 25 ports, and we are cross checking with not only one modes but different modes, like, and we are controlling the side lobe levels. We're basically, that is, we're optimizing it depending on the phase and what are the amplitude that has to be given at different elements. Okay. And the same antenna, we are going to see different solid lines and different angles, like azimuthal plane and the what are the main lobe levels, as well as the side lobe levels, and we are going to see based on the requirement, which what is the basically we are seeing, or you can see what is the performance antenna, and the same behavior will be seen in the real time also. And all these things cannot, all this analysis cannot be analyzed only through the means designing and manufacturing every time. It has to be so it has to we have to do through a simulation software, and this makes a little bit more appealing and reduces the effort of an engineer to bring out a high performance model. So I believe we have discussed about the phaser antenna as well as the user equipment, but one another feature that has to be create impact, because since we are using a wireless part, right, how it is being impacted with the human, that's our concern. We are using a telephone, right, and every time we are keeping it near to our ear, due to the exposure of electromagnetic radiation. What is the electromagnetic radiation? Is nothing but a electric field as well as the magnetic field varying electric field, and this electric field is going to interact with the water molecules present in the blood, and that is going to rise the temperature of the human body. So that's where we came across a SAR, or we call that one as a specific absorption rate. Specific absorption rate is the measure of the rate at which energy is being absorbed per unit mass by the human body when exposed to the electromagnetic radiation. Okay, so that's why every mobile or a user equipment that you see in the consumer products line, you see inside behind the box there will be something called SAR rating. Okay, you will be seeing 0.8 watt per kg, 0.891 watt per gram. So different mobiles are very different, but as per the government guidelines, it is mandatory. So all this analysis they are doing to these phantom models. They are taking a phantom model of human head and they are going to analyze that one depending on the radiation and method. We are going to see what is the distribution, temperature distribution uh, of the human along the human head due to the exposure of different equipments. So all this the analysis can be done also. Similarly, if we are going for a cancer treatment, you can see over here this is a cross section of a bone. You can see over here this is the bone, and we are going to see we are putting different antennas. Okay. Similarly, we are going to use for hyperthermia cancer treatment used to accelerate the chemotherapy. We are going to, no doubt, we are giving a key chemical, but how we are going to make it more effective? So we are giving a little bit high power electromagnetic radiations over here, okay? So as to kill the tumorous cells to bring out a very high fidelity means so that this radiation can be used properly. So this is being used for the cancer treatment. Cancer is nothing but a unwanted cells that is being grown in the any part of the human body. So that's the thing to kill the localized tumors. We are analyzing that one, and it's not the only energy that is important factor, but how much energy we are giving, that is inside the bone or the bone marrow, that is being calculated through the proper modeling of the phantom modeling of the bone marrow, as well as the human leg, skin, and everything materials you need to define, and we are going to calculate, see what is the temperature that is going to be inside that one. Okay, so in the previous slide we see that electromagnetic radiation will be harmful, but the same harmful effect can be used for human safety way or for a very dangerous thing or hazardous thing for the cancer treatment. Okay, it's a technology for which someone or you can say a evil for someone can be used for a proper and a positive way. That's the beauty of wireless thing. You can see over here, this device is being operated. It's a 4x4 antenna on the conformal structure over here. We are going to powerized from this end, and this device is operating at the 1.138 megahertz. We are going to excite at all the elements across the leg, okay, and we are going to bring out the focusing, okay, through different phases and different input powers. We are going to uh, bring out a focused an electromagnetic energy at a particular location, and this focused energy is going to kill the electromagnetic cells kill the tumorous cells inside the bone or a human body. And this analysis of this antenna, okay, that has to be designed through our tool called HFSS, high frequency structure simulator. It's a simple RF phased array applicator, and all this thing model has been modeled. The phantom model are available in the different websites and different internet, and we are going to use those models for our purposes. So this is the behavior of that antenna. It's not only the radiation and that has to be kept, but how long it has to be kept so as to rise to that temperature. Okay. So what is the time? In that time also important, because certain if the time you can see over here in the 6 minutes of time, it the temp at the localized thing the temperature reaches 47 degree. And but if you are going to keep further long, it might rise to 50 degree, and if you are going to make it 50 degree, then it is going to make it hazardous to other parts. So that's why we have to see what is the maximum time. So that's why in a multi-physics or mechanical environment, we have to see how much time we have to keep and we are going to see that only through the mechanical workbench or the ANSYS workbench. Now, this is one of the other example where we are talking about the EMI pulse generator, electromagnetic pulse generator, which will be used for now neurotechnology applications. They are using it. We are going to use a very small PCB structure, and it will be sending very minor signals so as for a spinal cord treatment and all that. Okay, and it's nothing but it's sending the electromagnetic pulses, okay, at a particular power and particular timing so as for a treatment. It's a kind of a physiotherapy, or you can say neural treatment. Okay, similarly, if you are using for the pulse generator and all, how it is being used for the MRI machines, right? So all these things and how it is being impacted at the MRI machine, all these things can be analyzed also. So all these things, it's not any kind of animation. These are all simulation that is being done in the ANSYS tools itself. And we are going to see what is the temperature and what is the pulse rise, what is the disturbance, everything. Okay, electromagnetic interference, everything is being analyzed in the tool itself. So I believe I've covered a little bit of phased array part and uh, how these arrays and can be used for technological advancement of human body, and it's not only limited to the device safety, or how we are modeling also, and how it is being used for different treatment of different things like MRI things and all. So this completes to come to the ends of the second phase. Okay, I would like to take any questions from your side. Okay, from afterwards I would what I'll do, I'll go for the third phase where I'll be talking about the designing of the reliable electronics, and how the design. I believe some one of your guy, one of from the participants, one of the person have gentlemen asked how we are going to design it. Definitely, I'll be covering that part, but I would like to take any question from your side if you have for design in the second phase. For the second phase, I'm open to take for the first phase also. Please feel free to put it in the chat window or to the host.
Oh, yeah, thank you, Sajid. That was really interactive session, and yeah, we'll wait for this question and answers part, and we'll see whether in case anyone has any questions, we'll try to answer that. You can drop your questions in the chat window, or you can unmute yourself, and you can directly speak to the speaker. You can directly ask to the speaker as well. Get answers for all your questions in case if you have any questions. Yeah, we got a question from Navya Susan. What might be the most appropriate array that provides a massive MIMO with less harmful effects in your opinion?
Pardon me, Ali.
Okay, sure. What might be the most appropriate array that provides a massive MIMO with less harmful effects in your opinion?
Okay. So generally, for a array, we are using a very planar array. It's like any kind of phased array we are taking. Okay. So the beauty of the phased array is like it doesn't need kind of, if your wireless device is moving, it's a dynamic in nature, then phased array can easily take it. But previously we used to have mechanical beam steering, but phased array gives a electronic steering. Okay, and definitely it whatever the radiations that is coming from the these arrays is harmful. You cannot avoid that one. So that's why we used to tell means don't means staying in a uh, highly electromagnetic exposure radiations might be a carcinogenic. So you can say the only way is to prevent a distance from that kind of a base station or wireless system. And exposure to electromagnetic radiations is in a longer exposure is a carcinogenic thing. Okay.
Okay, thank you. And we have one more question. So we cannot use phased array from upgrading a medical equipment. The same follow-up question from Navya Susan.
Mhm. Okay, so phased, you yes, indeed, you cannot design. I would not put like that way. You have to design a phased array in order to provide a user equipments. Like it's means in order to, it will be at the some far part in the top of the building, right? If you have a for a device thing, there are multiple devices there in your room, right? So you will have your the base station part at the top of the building, right? So it's like we have to keep the like that way. So you are seeing that for a base station, you can take a analogy of a base station. You can say the base station will have a very top distance, very high, and it will be covering a completely one area. Inside that area, there will be many cell phones that will be connected. Similarly, for MIMO applications, you will have very small phased array on the top of your building, okay, and that will be connected to the complete wireless system, okay. That will going to uh, be like a modern kind of structure or a router kind of structure, okay.
Yeah, thank you, Satya. And we have a question from SG Ratnamala. So, what is the source of noise in EMI pulse generator?
The source of noise is nothing but different there are many noise. It's not, I'm going to cover that one, what might be the source of noise, that I will be covering definitely, but I'll give a little bit of insight. There are three factors that are going to make a noise. That is signal integrity, power integrity, as well as the external radiation. So all these three things are making are the sources of a electromagnetic interference. There might be a some kind of unreliable structure that is there where signal is making an interference. Okay, from the inside the system, there will be another thing. Suppose you are near to the MRI machine. You the doctor or any other person took a mobile phone. Definitely, the radiation from the mobile phone is going to interfere with the MRI machine. So we have to bring out that kind of device which will have very less impact. I won't say we cannot remove the impact completely, but very less impact so that our device cannot be affected in order to make an electromagnetic interference.
Thank you, Satya. And we have a question from Lelisa. So, can we perform analysis the kidney infection from ultrasound using ANSYS simulation, and how?
Okay, ultrasound. I believe ultrasound itself is coming to see whatever the RF frequency that is ranging from 300 300 kilohertz to somewhere around 30 gigahertz. So I believe ultrasound doesn't comes in that frequency band. Okay, but yes, indeed, for the kidney analysis and all that. We are going through ultrasound method. So ultrasound, what they are doing in the ultrasound. So for the ultrasound, it is sending us a sound wave. Ultrasound is nothing but a sound wave. Okay, sound wave is sending inside our body, and whatever the reflection that is coming out from that one. Okay, if there is a stone, okay, that is present in the so the stone will have a different kind of reflection, but and our bone or skin will have a different kind of reflection for the body for the in response to the sound wave, right? So depending on the reflections of the sound wave, it is detecting, and we are going to detect the size of the object, and or you can say what is the size, or what is the what might be the you can say orientation. So that's why ultrasound is being used for what is the position of the a pregnant baby, a pregnant lady, the baby is there. So we can, through the ultrasound also, we are going to see the structure. So it's nothing but a sound wave. So I believe ultrasound frequency and the RF wireless frequency doesn't comes into that frequency range.
Well, thank you so much, Satya, for that. So, well, in case if you have any questions, you can even unmute yourself and you can directly ask to the speaker and get your queries resolved. Yeah. Uh, we have a question here from Navya Susan. Is there any limitations to the spectrum range that we can test using ANSYS?
Uh, we don't have any kind of limitations. Okay, basically, for the RF and all that, it comes into frequency range for the 30. Suppose you are operating in a RF and electromagnetics range, so it has to be go through the 30 megahertz, 30 kilohertz to 30 gigahertz. It's very frequency broad range, but if you're going 30 gigahertz, it comes to the into the infrared, ultrasound, or any kind of a giga. It's a terahertz spectrum. But if you go beyond that, less than 30 gigahertz, means it's like a sound wave or any kind of frequency. Okay, it's not a electromagnetic wave we would call. Okay, so in order to understand that and that phenomena, there are other different tools out there, like we have ANSYS mechanical, or for understanding the acoustics things. Okay, in order to understand the optics phenomena, we have an optics tool. Okay, so there are so in order to capture that one, ANSYS has a very
Satya, we cannot hear you. I'm not able to hear you for some reason.
to perform that kind of analysis. So it's not only, we would say, that tool is
Satya, I'm so sorry to interrupt you in between. We're not able to hear you in between, like your voice is breaking. So would you mind repeating the answer again?
hello.
Yes,
Hello, Ali.
Satya. Yeah,
Yes,
now I
yes.
can hear you. But in between, while you were delivering the session, like between multiple times, your voice was breaking. So could you please try to answer that? So that, you know,
Okay.
yeah.
Okay. It's not only single tool. See, simulation tool is nothing but a black box. Okay. So whenever we are choosing any kind of tool for a particular frequency range, we have to understand, we have to know what we are doing. Okay. So for a different frequency range, there are different tools out there. And for acoustic wave analysis, we have a different tool. For electromagnetic wave analysis, we have electromagnetic tool. For optical analysis, we have a different tool. It's like that way we have to figure it out. Okay. So all these waves has a different phenomena and different behavior. Okay. We, as an electronics part, we only deal with the electric field and magnetic field. Okay, it doesn't have any kind of sounds or anything, sound impact on it. But if you are dealing with the acoustic waves, right? So if you are dealing with the acoustic waves, then we have to deal with any different tool called ANSYS mechanical. There are that phenomena is there. But if you're doing for a visible spectrum, so the visible spectrum, what we are seeing is that comes into the range of terahertz. So for that one, we have a different analysis tool called the terahertz technology, or optical tool is there. Okay, so we have to choose judiciously.
So thank you so much, Satya, for that. Any questions you can drop here, or else we can go ahead with the third phase of the session. Satya, it seems we have these many questions, so I think you can go ahead with the third phase.
Okay, sure. Thank you, Ali. Okay, now we are coming. What are the challenges and for designing a reliable modeling? Okay, in the reliable modeling, I believe one of you has asked, are you able? Are you going to? Are you going to able to design that kind of structure? Right? Ali, I believe that.
Just give me a moment. Let me check that. Yeah, I think you're clear. You can go ahead, Satya.
Okay, thank you, Ali. Thank you for the support. Okay, so I believe one of your means one of our gentlemen asked how we are going to design those kind of structures. Are you going to able to design the structures? So while designing any kind of a electronic industry, so PCB is nothing but a printed circuit board. Okay, it's one of the most complicated design in the electronic industry. Undoubtedly, it is little bit tricky, it's not only limited to one layers. It's PCB, a simple PCB. You can say that a laptop or a computer motherboard. It looks like a motherboard will have very complex chipsets, as well as you can say like I've taken one very small PCB. You can see over here. It's a 3D picture. Okay, there will be many connectors for a USB, for an audio jack. There will be a part of processor, and these are the RAMs over here, random access memory, and the coolant part, and other connectors. Like then it will have a copper traces. You can see over here, and registers, capacitors, and different parts will be there. Okay, and you can see over here. So this looks like a very in the real world, but when it comes to the electronics world, okay, all this will have a connected. Will have copper traces. You can see over here. There are many copper traces are there connected to different segments, and it is indeed important that whatever the signal we are sending from here to here, that should go accurately. And if since we are dealing with the electronic digital signal 1 or 0, okay, so multiple signals will be going at different things. So multiple signals will, there might be a chance that there will be multiple impact and it might deteriorate the signal. So in order to show that one, so we have the three things. Okay, we have to see, in order to design that one, we have to see what is the electrical reliability, thermal reliability, as well as the mechanical reliability. Electrical reliability, we are going to deal with the power at the signal integrity. Means what are the power and signal is there inside the PCB. Thermal reliability, due to the power and signal that we are sending, what is the heating effect? Suppose heating effect, if any of you are using a cell phone, and if you are using it for very longer time, like a 30 15 minutes, 30 minutes, or 1 hour, you can see that there will be a rise in the temperature, right? So this is nothing but heating effect. So that's why we have, and if we are going to, the temperature of the device is being raised, at the same moment the device has to perform at that temperature. Otherwise there might be issue, because since the chipsets are there, they might perform it differently in different, but if you are going the rise in temperature, definitely there will be a thermal effect, sorry, mechanical effect, because this temperature is going to create the stress on the board, right? So that's where the mechanical reliability also comes. So for while designing the boards, we have to see the three aspects. But from the electrical perspective, we have to see the signal and power integrity analysis. From the thermal perspective, we have to see the thermal analysis, where we are going to see the different temperatures. And from the mechanical things, we are going to see what is the bending effect or the warp phase analysis. Okay, I'll be covering that part in all three parts in coming sessions. First, we'll be talking about the electrical part. Okay, you can see over here. This is what means. Basically, I want to clarify what is signal and power integrity. Okay, so if we are sending one signal from one point to another point, okay, this is the connector, and it will be traveling multiple paths over here, and it will be ending to one of the point, right? And it by the time it has to connect it to a different components like connectors, PCB traces, microchip, a connector, again the resistor, and all that. Okay, all will have individual losses and all things. So that's why when we are sending a signal from one, if you are sending a digital signal one, by the time it reaches to here, whether it is reaching one or not, okay, what is the power of the signal that is being reached over here? Because at certain power only these devices are going to operate, although it's a very low power, but at certain power the minimum threshold has to be covered, otherwise it is not going to work properly. So that's where we call that one as signal as well as the power integrity. So we have to see whatever the signal we are coming from one side, from the transmitter side to the receiver side, it is going to reach properly or not. So that's where we are going. So suppose there is a system is there where transmitter module is there as well as the receiver part is there. From the transmitter to the receiver, there are multiple parts like a chipset module, PCB, a connector, again a PCB, again a module. So this is a very common part of the path how the signal will be traveling, right? Multiple parts of the PCB. But the moment it goes from one module to another module, you can see over here the signal is going to be deteriorated after due to many reasons. That might be electrical loss or external environment loss, and this creates some signal integrity and power integrity issues. So we have to see. So in the real phenomena, what is happening? Okay, you can see over here, we have a transmitter circuit, we have a receiver circuit. Okay, the transmitter contains a module will be like this, a PCB will have multiple parts like copper traces and the connector. Okay, over like USB connector or anything. And again to the PCB, again a module and all that. So we are going to see whether our signal is reaching properly or not. Okay, because there will be multiple information that will be transferring at the single moment of time. Since we are talking about the in the starting of the session, I talk about 64-bit or 128-bit or 256-bit. Bit means at the simultaneously it is sending 256 bits. Okay, 256 gigabits of saying at the same in 1 second. So that's the high speed. So during that high speed also we have to see what is a signal that is remaining at that level. Okay, so you can see over here this one cycle is nothing but in the order of 1 nanosecond. Okay, you can see how much reliable analysis and how much extent we are going for the analysis. So how a PCB works, I am going to tell. You can see over here. So there will be multiple transmitters, multiple receivers. We are sending very fast signals, and definitely multiple signals interfere with multiple signals, and it is going to create a different resonances and power issues and signal integrity power into it. So and due to multiple signals, there will be crossed off with each other. That's why we have to design a very proper way so that there will be a signal integrity and power. There shouldn't be any kind of signal integrity issue or a power integrity issue. You can so any kind of poor SI or signal integrity and PI power integrity design creates electronic noise that can become a electromagnetic interference. Okay, I believe I'm trying to answer whatever the gentleman asked, and which are and proper placement of the decoupling capacitors. Generally, in order to do the power integrity analysis, we have to keep a decoupling things. For that, we are going to put as a capacitors between lines so as to bring out a to avoid the power integrity issues. So if we come across a very small antenna theory, you can see over here a simple antenna loop is there, and if antenna is loop means a simple wireless path, a wire current path is there, and that path is going to radiate. Okay, so this is, and if there are two modes like the differential mode and the common mode. Okay, and this loop kind of phenomena will, because you can see over here, just give me a second. So this signal is not only transmitting from one side. If there are designs of multiple PCB, this signal might be a different, taking different orientations on the PCB, right? You can see over here, I'm going to take a little backwards to give a little bit insight over here. Yes, you can see over here, it's not only straight only it is traveling. It might travel to multiple ways, right? Okay, and if there is a cyclic way, so the moment the current what is traveling gives a cyclic way, it creates a loop kind of thing, and loop creates means it is going to radiate. Okay, and the radiation that is coming from the PCB is going to make an impact for the electromagnetic interference. You can see over here. I'm going to yes. You can see over here. There will be one current that is going from one end to another end, and similarly, one current that is coming from the same current is being used from this end to this end. You can see over here one end to going this side, another one. So this creates a loop over here, and this loop is going to act like an antenna. Okay, this is nothing but we call in the electronic terminology, it's a common mode, and this loop is nothing but behaving like a dipole, and it creates an electromagnetic interference kind of phenomena. So to design a PCB electrical signals, there are three aspects. One, we have to do the power integrity analysis, which comes in the DCIR analysis or the direct current analysis, resistance analysis, impedance profile. We are going to see. So there are different levels of analysis how we are going to do power integrity, and we are going to the signal integrity, where we will be seeing the impedance, crosstalk, reflection, termination, and the dielectric loss. Then finally, if there is some kind of noise is there, that is electromagnetic interference or the electromagnetic compatibility. So electromagnetic interference, I believe, is nothing but the summation of power integrity issues, signal integrity issues, as well as the antenna effect. Okay, so this comes into the perspective of electrical reliability analysis. All this we have to do. You can see over, we are taking a very generic example over here, because nowadays, if you going for any industry, cell phone is the most common thing, and cell phone will have a small antenna that will have radiations. Okay, and we are going to see how this radiation is going to make an impact. Okay, so this antenna array will have a uh, which have a radiation and a simple controller part. Okay, and a DDR module. This module, whatever we are going to see, is the DDR module we are going to see. You can see over here, when it is operating in normal conditions, you can see over here the signal that whatever you are sending, it is making an impact of yes, we are sending a proper signal. Okay, and here the antenna system is being not activated. Okay, but you can see the moment the antenna, if you are changing a very beam, okay, at a different, depending on the requirement, we are rotating it to achieve the signal. You can see over here that whatever the signal is, this beam is going to make an effect on this signal. You can see over here in the real time. Okay, so all this analysis has been done in the ANSYS tool itself to provide a little bit insight, real time insight. You can see over the moment it reaches the radiation, it deteriorates the signal over here. Okay, you can see there is most deterioration on the signal. I believe whatever the results, it's much more appealing, and I'm making a little bit understanding that what it is being happening over here in this phenomena. I believe I have answered how electromagnetic interference is making a disturbance. What might be the so this is the answer, how the self electromagnetic radiation or the external radiation is going to make an impact on the signals. So that's where the electrical reliability comes. So moving to the next part, from the electrical reliability to the thermal reliability. Okay, so thermal reliability, we have to dealing with the, because due to the excess usage, continuous usage, uh, the temperature is being raised, right? So you can see over here, if you if it is goes for a little bit longer time, okay, so there might be a catastrophic failure like burnout issues, or some kind of chip will be burned out, right? Okay, it might be a malfunctioning. So that's what we call, due to the higher temperature, and we call this one in the electronic industry is the Joule heating or the resistive heating, where the temperature is being raised due to I square R losses. I square is the I is the current, and what is the resistance? So what is the temperature when it is going to burnt out? Okay, so Joule heating is nothing but the heating in the process. Joule heating or the resistive heating is a process by which the passage of the electrical current through a conductor of the electrical resistor releases heat. Due to the excessive heat, it burns out the soldering, that is the chip is being done over here. So that's what malfunctioning, or that's what happened in a continuous usage of a any kind of a PCB board. You can see over here, in if you are using for continuously, definitely the power is being utilized. So for that, to see the power is nothing but voltage multiplied by current. So we are going to see what is the voltage on the PCB, what is the current in the PCB, then finally multiplied both the thing, and we are going to see the power, and power we are going to see the what is the thermal phenomena on the PCB over here. Okay, so we have to see at the starting whether our PCB is meeting our electrical requirements. Then finally, we are going to the thermal influence, because this electrical requirements is mandatory to have a thermal influence. So that's why we have to make sure that it's not only electrical perspective but also the thermal perspective. It has to be performed in a better way. So you can see over here, this is one example where we are taking very minor voltage. You can see over here a 1.8 volt we are taking, but the power is 17 amps inside the PCB. Okay, and we are seeing the source, and we are seeing the what is the power source, power and the current density plots at the different layers of the PCB. And you can see over here, due to the excessive temperature, and we are seeing that hotspot zones on the different, and we can see in the different planes. So ANSYS iSpec is a tool where we can see the temperature effect in that for the thermal aspects of. You can see over here in the for the, and once it creates the thermal aspects over here, you can see the mechanical, definitely the rise in temperature. Once the temperature rises means the coefficient of thermal expansion at the different layers are different. So due to the different expansion, these layers expand at a different lengths, and this will create rise to a bending effect. Okay, so that deformation is nothing but a mechanic PCB warpage. Okay, that analysis is being done in the ANSYS mechanical through the static structural analysis. And whatever the results we are getting from the HFSS and or the SI wave for the PCB analysis to the ANSYS workbench, we are going to send not only to the data but also geometry. So these geometries are the user need not to worry about the transfer of the data. ANSYS Workbench provides a platform in a ready-to-solve model. You can say just a drag and drop approach kind of thing, and your model will be for the multi-physics will be ready. You can see over here board this whatever I've discussed is the board level warpage analysis due to the mismatch of coefficient of thermal expansion. The stress will be created at different shoulder joints or the interconnects, and excessive warpage can lead to a weaker joints. Okay, at a different bending and all the things at different bendings, because there are multiple layers, and this bending will create some kind of a you can say mechanical stress at the different shoulder joints, and this will give rise to a bending effect. Okay, and this then what will happen, this bending effect will bend the structures in a very random phenomena. Then finally to the mechanical reliability. Okay, we spoke about the electrical part as well as the thermal part. Then we are moving to the mechanical part. What are the other part, external mechanical phenomena that is going to create an impact? So you can see for the mechanical analysis, we are going to put this PCB on a very different harsh environments, because it's not a very ideal environment. Suppose we are putting a PCB on a in a vehicle, or it might be in a you can say inside a biomedical equipment, and the biomedical equipment is going to, if it is a static properly, it's okay. But if it is in dynamic pressure, we have to move it in a different location and all that. So this will create a resonance in this thing. Okay, so in order to do that, we have to do the modal analysis for the basic vibration analysis. Okay, that's what we call, and commonly used for the vibration analysis. And this vibration is also going to create some kind of impact on the PCBs or any kind of electronic components. So these are the external mechanical noises we call. Okay, and these noises are being, there are random inputs are there, but due to it's a natural phenomena. If we are going to distribute on a different frequency band, these noises are nothing but it's in the spectral curve. If you are going to make these noises into Fourier transform, this comes into the Gaussian curve. Okay, so we do at different amplitudes and different frequencies, we do the random signals, and we bring out the power spectral density analysis, or you can say we are doing instead of statistical in the sampling time, we convert it into frequency domain, and we do the PSD analysis for the statistical, because this is a natural phenomena. We are creating a random noises and converting in the frequency domain, and since this frequency domain, we are analyzing that random vibration in the frequency domain, and you can see the inputs are natural frequencies and natural modes, and input there is the PSD curve, and we are going to see at different modes what are the stress levels. That's what we are calling is the first mode, second mode, and third mode. So these are the nothing but the eigen modes or the natural vibration frequency. That's what. So basically, these are some kind of acoustic waves, or you can say random natural waves. We are going to see the mechanical reliability. So I believe I have a little bit covered on the how electrical reliability is the mechanical or thermal reliability as well as the mechanical reliability. So finally, so while addressing all the engineering challenges, we can see that all these products like a smart glass or a Bluetooth, a user equipment or a Fitbit, all these things can be analyzed through a simulation-driven product development process. It's not only limited to some kind of a wireless lens or a hearing aid, or you can see a pacemaker for calculation of specific absorption rate, or a wireless MRI machine or smartwatch. So all these things can be covered all together in a wireless environments. So, coming to the end, we are looking as a predictive or the preventive and the personalized participatory, or we call that one as a P4 medicine. And this P4 medicine is safe and providing a better society in the coming world. And this all signal integrity, power integrity, and all this equipment interference, right? All the electronic interference reliability, or the what is the behavior of electromagnetic wave on the human patient body. We are going to see, we have seen the interactions, and based on standards, what are the government, as per the government norms, we can design our products over here. So it's, you can see over here the power. So power, we can see that reduction in the power, dynamic power reductions, electrostatic discharge, wireless power charging, all these things can be done. And the antennas, you can see EMI, EMA compliance, channel modeling, antenna integration. So we have covered all these individual topics, individual by individual, to see how all means how a simulation driven product development can be addressed. Finally, it's not only the hardware devices or the electronic industry, embedded software is also needed so as to see control panels or the display parts, because basically this is a user interface. So we have to design a proper user interface in order to make this wireless device act function properly. Then finally, to the structure, we have seen the structural reliability as well as the thermal reliability, where we are seeing the strength analysis, vibration. Similarly, we can do the vibration drop analysis, and we are going to see, we have seen the electrothermal analysis also. So finally, it's not how we are going to bring out the safe and reliable electronic devices to the body interactions. So all this, and in so different data mapping techniques from the multi-physics environment. Just give me a second. Ali, just give me a second. There is a noise. I have to from my end, so I have to stop a little bit. Just give me a couple of seconds, okay?
Oh, sure, sure.
Yeah, thank you, Ali. Thank you, gentlemen. Actually, there is a. I'm working from home, and there are frequent noises are there, so I have to stop. Okay. So, in order to bring out, coming to the point, in order to bring a reliable electronics, it has to go through a electromagnetic analysis. It has to go through a mechanical analysis, a structural analysis, as well as the fluid analysis. So, all these things means the data, whatever the electromagnetic data has to be read with another tool. All this, and the thermal data has to go through a structural tool, and the structural data has to go through. All these are interlinked, and this gives an ANSYS multiphysics platform, gives a platform to bring out the most robust electronics around the throughout the complete simulation, by implementing different physics and different tools for individual physics, and so that whatever the, and all these devices are being optimized individually at a different from different perspective, and the different tools. We are optimizing mechanically, we are optimizing the electromagnetically and thermally, all this thing optimized to bring out a optimization technique, and we can implement the Six Sigma so that our cost can be also reduced. And based on that one, we are bringing out a you can say 3D mapping. This 3D mapping helps us to bring out the most cost-effective product. So if you are putting some kind of requirement to bring out reliability, actually like couple of multi-physics analysis and automated data and accurate data transfer within the tool, within the system, and definitely these are our requirements. And once we are using this ANSYS platform, we are getting implementing these requirements, we are getting the most benefit, we are bringing out most benefits, like we are ensuring the product performance across and beyond the performance envelope, right? So ANSYS is the one of the platform is way ahead uh, ahead of the simulation industry, and bringing out multi-physics analysis reduce the failure modes due to the system interactions. Since we are going through multiple systems, okay, multiple you can say simulation tools, the product failure what you are bringing also, we are making a less probability. Okay, I would not say that it's 100%. I would say that less probability, and because of its most effective way of designing through different platforms. Okay, and we have created a different platform that can support different multiple variants also. So this is one of the video again. What ANSYS is capable of. Okay, I will be playing. Probably there is might be an audio issue, which we have seen earlier. Here I will be explaining the things that are being there. Okay. So this video talks about the design flow of a wireless device in complex RF environments. Okay. Yes. So just give me a second. There might be a yes. Yes. So three things that matter most is the in the wireless environments is the antenna, antenna, and antenna. So all these devices from the router, smartphone, and any kind of a thing, smart ball, all this contains an antenna only. Okay. And those things, wireless environments, are kept in a different and kind of environments. This is a smart home, okay, where multiple devices been kept, okay, a smart bulb, ipad, a router, a wireless printer. You can see over here in the environment there will be wireless bluetooth speaker, uh, uh, different wireless parts are there. All these are being simulated through different things, and all these things contain one common thing is called the antenna. So designing one of the most proper antenna is also an important factor. And in a putting in a different putting in a different kind of environments is also makes an impact. So so in ANSYS, how the electronics things shift since there are multiple antenna systems. Suppose if you are designing one antenna system, you are going to use a ANSYS tool called HFSS, high frequency structure simulator. But if you are going to position that system, we are going to use the Savant, which uses on the very big environments or very large products. If there are multiple antenna systems like interfering with one antenna system is going to interact with another antenna system. Okay, here what is the interference between the system that can be calculated to the emit. Okay. Here, this is our smartphone antenna. Here, this antenna contains a GPS and a Wi-Fi. You can see where the antenna is being extended to different things and connected to power. And we are going to see what is the power is there. Okay, how the power is being transferred properly, and what depending on the thing. And this antenna is being analyzed in the HFSS. You can see over here, we are going to analyze different antennas like for the cellular and the wideband as well Wi-Fi band and the GPS band. And we are going to see the S parameter value over here. Okay. Once we are going to design the 2 to 3 systems in a single platform, we are going to create an emit project. Okay, in the electromagnetic interference kit we are going to see the what are multiple antenna systems are being analyzed. Okay, because multiple antenna systems are going to interfere with each other. Okay, so this we are just going to create 2D models, okay, for different antennas, and we're going to calculate what is the interference between each other. Okay, so this is in the same antenna system is being implemented where a Wi-Fi module and the antenna is there and the filter is there, and you can see the multiple antenna systems how it is being interfering with each other. And you can see over here multiple antenna systems are we are going to create. Okay, matrix method over here, and green matrix that yes the results being it is not interfering, but if there is a red part is there, yes it is interfering with each other. Okay. Similarly for the Savant, it's nothing but putting those antenna systems in a different environments, big environments like a house. You can see over here the small antenna kit is being put at different parts. There is wireless PCB printer is there, and the same antenna is being kept in a different environment. Okay, what is the performance or what is the real-time phenomena of the electromagnetic radiation that can be seen in the Savant? Okay. So these things are being analyzed in a electrically large environments. Okay, you can see the multiple antenna systems are there to see the real-time effect. And while the user is moving, also we are seeing the real-time phenomena how it is being infected at to the level how much electromagnetic radiation is big there. Okay, it's like if we are putting a router on a one part of the home, and that router. Just give me a second. Okay, if you are putting a router at one corner of the home, so at the one corner we are seeing that we are getting a poor signal, but the moment we are standing in the line of sight of the router, then we are getting a very clear signal. But if there is some kind of a blockage is there, again if there is a blockage, we are getting a less amount of signals. So that's all this analysis can be done using the ANSYS tool called Savant. So you can see over here, yeah, you can see over here, HFSS can be used, ANSYS HFSS can be used for a user equipment, but if you are going for a multi-system analysis, you can see over here, we are modeling the multiple systems, we are going to see the interference, we are using the emit, and if you are going for a uh, very large environment, then we are going to use it for okay, and we are going to see the real-time performance of the radiations and what is the radiation level, what is the electromagnetic signal that we are getting. So thank you for, I believe this video of ANSYS is gives a little bit insight. Okay, you can see over here. So this comes to the means moving towards the conclusion part. So you can see over here, similarly, if a base station is there and multiple cars are moving, connected cars are moving, and these connected radiations are being watched, okay, through the electromagnetic beam steering method, you can see that in the spatial environment, how we are going to see the objects are moving, okay, from base station end, how the base station is seeing that, yes, this object is being moved at the different space. So you can see that over here. So, coming to the conclusion part, ANSYS simulation tools are used across all the industries of 5G, and array analysis like finite array analysis or the base station analysis, like finite array domain decomposition techniques are used for array synthesis. Okay, using the method of periodic mesh or the copying mesh technique. Then this brings a comprehensive as well as the accurate solution to bring out the best user equipment, not only limited to user equipment but also the base station. Okay. Similarly, we are going to change the means physics-based tunnel modelings like using the Savant or the SBR plus to bring out the dynamic link and the higher fidelity antenna. And we are going to see the for a MIMO environment, multiple inputs and multiple outputs. Okay, so massive number of users also can be accommodated in the base station to bring out means you can see that what is the signal processing capability also that can be in the spatial domain that can be also being seen can be seen. So similar other part means this is a continued conclusion. You can see that ANSYS multiphysics capabilities can be combined with our expertise with the human body like SAR interactions and all that, and which enables the users to accurately model for biomedical performance in order to have a real world by incorporating real scenarios, by incorporating the electrical, thermal, as well as the mechanical effects to improve the reliability of the PCB. And there are many ways to model that depending on the relevant physics in the biomedical market, like two-way couplings between HFSS and workbench can be done, and one-way thermal link between HFSS and Fluent. Fluent is being used. Fluent is the one of the tool from the ANSYS which is being used for the CFD technique for thermal analysis. Okay, we can use for that analysis for the multiple, and you can see that system level analysis can bring out the higher fidelity models so that it can run for longer time. And ANSYS Workbench gives you the integrated and drag and drop approach to bring out a very smooth design analysis. So this comes to the end of the third phase, I believe, and we come to the conclusive part of the our session, which is based on the charging medical device for system reliability efficacy. Now, as a CAD firm, we believe that simulation is more than a software, because it's not the simulation tool. How you're using the simulation tool also creates an impact, right? So software is nothing but a black box. How we are doing the simulation, depending on the requirement. Suppose we are going for a thermal analysis, then we have to use this tool. Then if we are going for a mechanical analysis, we have to use ANSYS mechanical. Suppose we are using a electromagnetic analysis, we have to use okay. So I believe, as one of you have asked, that how we are going to choose the tool. So if you can feel free to write to me that how we have to use this tool, and probably we are there to guide you to make your things possible. And we believe that simulation is indeed our superpower. That's what.
Thank you, Satya. That was really a nice and wonderful session. So let's see whether, in case anyone has any questions, so that we can quickly answer their questions. So, in case if you have any questions, you can drop all your questions in the chat window to the host. We will try to take up each and every question. We will try to take up each and every question one after another. So, or even you can unmute yourself and you can directly ask to the speaker. Satya, let's see, in case if anyone has any questions, we'll try to answer them.
Sure.
So I think we have these many questions. Okay, we got a question from M. Praveen Kumar. So, sir, how do we validate our results with regard to a life cycle analysis of the PCB under various conditions?
Okay, so for I believe for a life cycle analysis, suppose you are dealing with a very means you are dealing with a life cycle, right? So how much cycles it is? So there is one tool with us called Serlock. So basically, the Serlock library is being so designed that uh, how much life cycle it has to pass. Then there is a tool, and based on the life cycle predictions, we have the library, and we can predict what is the life cycle based by how many million times a device is going to work and all. So all these things, just to give a moment, I'm a little bit adding something to showcase. Yes.
Satya, you need to present your screen.
Yes, just give me a second. Give me a second. Just. Okay, just give me a second. So are you able to see the screen?
Yeah, I'm able to see it. Great.
Yeah, great. So you can see over here, ANSYS has a very diversified portfolio. Since multi-physics and multi-analysis are being coming from, I have not added this slide, okay, but thank you for giving a little bit of buffer, but I added this slide. So depending on the platform, we have different tools like fluids for the different tools are there for different levels of analysis. Similarly, for mechanical structure analysis, we have tool called ANSYS Mechanical, Autodyne, LS-DYNA. For the electromagnetic analysis, we have HFSS, Maxwell Q3D. Similarly, one of you have asked like how being used for optics. So there are different tools are there, okay, ANSYS. And for semiconductors, similarly, we have for reliability analysis or the life cycle prediction, we have one tool called Serlock. Okay, so this Serlock gives a life cycle prediction. Okay, life cycle analysis. Just I'm pulling out. Just give me a little bit buffer. I'm pulling out that slide. Okay.
Hi Satya, I'm so sorry to say your voice is not audible. Satya, could you please check once that we're not able to hear you for some reason? Satya, can you hear me? Satya, I'm so sorry for interrupting you in between. So I'm not able to hear you. Satya, can you hear me? I'm so sorry for the inconvenience, guys. So let me check with Satya whether what exact issue is happening. Uh, Guys, please allow us a moment. Satya, he is configuring something, so he's about to connect in a moment. He's checking some, he's troubleshooting his audio.
Hello, Ali.
Yeah, Satya, I can hear you now. Yeah, please go ahead.
That I believe that this is some kind of technical glitch that happened. Okay, so just give me a second to share my screen. So I believe I got stuck in this slide, right?
Yeah, exactly. Yes.
Okay, so basically, I was talking this. There is a tool called Sherlock, which has already the library is there for different type of components like solder joints and capacitors, ECV, and all that. There is one of the very powerful pre and post processor is there, so that once we design with the analysis to different techniques, okay, all the thermal aspects and all that, depending on the temperature need, okay, this solves the how much life cycle is being there. Okay, so this curve contains like all the modules like thermal data, mechanical data, and the electronic data. All this data is there, and depending on the data is there, and we are going to see the what is the life cycle, and we can predict that one also. Okay, so that this will reduce the warranty cost. So there is a tool indeed. Okay, and we can see the what is the life cycle prediction for the any kind of electronic tool, electronic gadget. Okay, it is there indeed.
Thank you, Satya. Thank you for that. Well, in case if you have any questions, you can directly unmute yourself and you can directly ask to the speaker. So, or else even you can drop your questions in the chat windows. We can quickly take up each and every question.
So I would like to. I'm in my previous presentation. I missed the slide. You can see over here in the ANSYS tweet our president and CEO throughout the world. Okay, he sits in US Pittsburgh, and he commented that yes, and I'm just reiterating the statement: simulation is our superpower, and we know what we are doing, and we provide all the round of solution across any physics. And it's being tweeted in 11th June 2020. Okay, and simulation is our superpower. If anybody is there in Twitter, please visit. You can see that you can tweet over there, subscribe for the answers, and you can see that this comment is always there. Okay, I've taken just a snapshot from the Twitter.
Great. Yeah. Thank you, Satya. So I hope we have uh, yeah these many questions. Yes. Well, however, I have dropped our details. Like, in case if you have any questions, you can reach us at any time on our marketing mail ID, marketing@catfm.in, or even you can call us at 984 999 8435. Please feel free to reach us. It's a pleasure to give the proper assistance.
Hello, Ali.
Yeah, Satya.
Uh,
Well,
so, uh,
yeah. I think we have these many questions.
So, Ali, if you are running out of time, or if you then probably we can take the questions offline also. You can write. Please feel free to write to our marketing, the catfm.in, and you very soon, like within very less moment of time, or you can say as soon as possible, you can get your answers back. Okay.
Yeah, I have dropped all the details here in the chat window. Please go through those details. Like you can reach us at marketing, email ID marketing@catfm.in, or even you can call us at 984 999 8435. So you please feel free to reach us at any time. Thank you so much once again. Have a nice day ahead. Thank you so much for your time and patience once again.
Yeah,
Yeah,
I
have a great
appreciate.
day ahead.
Yeah, I appreciate all you for joining our session. Okay. Please subscribe to in our connect to our LinkedIn, and you will be getting notified. Thank you. Have a great day. Bye bye.